Hello everyone, let's talk about another medium problem on Leetcode today. Range sum of sorted subarray sums, Leetcode 1508. In this problem, we are given an array nums consisting of n positive integers. We have to compute the sum of all non-empty continuous subarrays from the array and then sort them in non-decreasing order, creating a new array of size n into n plus 1 by 2 numbers. Then we have to return the sum of numbers from index left to index right, index from 1 inclusive in the new array. Since the answer can be a huge number, we have to return it modulo 10 to the power of 9 plus 7. So now let's look at the examples to understand this problem better. In example 1, we can see that nums is equal to 1, 2, 3, 4 and n is equal to 4. Left is equal to 1 and right is equal to 5. So from nums array, we can see that these are the subarray sums that we can calculate. Suppose we start from left to right, then we take 1, then we take 1 and 2 and sum them up. Then we take 1 and 2 and 3 and sum them up. And then 1 plus 2 plus 3 plus 4. So that's how we will get 1, 3, 6, 10. Similarly, from 2 we will get 2, 5, 9. From 3 we will get 3 and 7. And then from 4 we can only get 4. So then we sort it. So this is how the sorted array looks. And now we have to get the sum of all the values between indices left and right. Because it's one index, we start from left equal to 1 and then go all the way up to right equal to 5. So we start counting from 1. So it will be 1, 2, 3, 4, 5. So the right will be at 4. So when we sum up all the elements from 1 to 4, we will get 13 as an answer. And in this case, we don't have to use any modulo operator, but if the sum is very large, then we have to use modulo 10 to the power of 9 plus 7. And in terms of solution, one of the easiest way to solve this problem is what we saw in the example. And then as a follow-up, we can actually use a heap to improve the solution. So let's first code this naive solution. So first thing we will do is we will create the list of subarray sums. Then we don't have to worry about indices. We will just append the elements. Then we will start filling in the values in the subarray sums. We are already given n. In the outer loop, we will select the index from where we want to start the sum. And in the nested loop, we will actually accumulate the sum up to n. So suppose we take 1, then we do 1 plus 2, then 1 plus 2 plus 3. So that's how we calculate the current subarray sum. And then we will just append it to the list of subarray sums. Now we sort the list of subarray sums using collections.sort. And then we just need the answer. So I'm just taking long to avoid overflow. And because this problem is one indexed and our subarray sums is 0 index, so we will just do left minus 1. Similarly, we can either do I less than equal to right minus 1, or because it is an inclusive index, or we can just do I less than right? So once we do that, we will just do I plus plus and update our answer. And then we will mod it using modulo operator. Let's define mod as well, because it's 10 to the power of 9, right? So we will need 9 zeros and then replace last 0 with 7. And that's it. And now we will just return the answer by converting it to integer first. And that's it. Now let's run this code. Awesome. Let's submit this code. Cool. In terms of time complexity, it is O of n squared log n. And the reason for this is when we build this array that takes O of n squared time, and then we sort them because there are n into n plus 1 by 2 elements. So roughly there are n square elements. So when we sort it, it becomes O of n square log n square, and it will be O of n square log n because it will become 2 log n, and that's why it is O of n square log n. And in terms of space complexity also, it is O of n square because we are storing these elements in the subarray sums, and that's why the space complexity is O of n square. And the question is, can we do better? And the answer is yes. So if we look at our sorted subarray sums array, we only care about the values between left and right pointers, right? So everything after right or anything before left is not useful to us. So can we actually use some approach where we can actually get the values just up to the right pointer or just between left and right pointer? And the answer is yes. Actually, we can use a min heap for that, similar to what we do in generate nth ugly number, if you know that problem. So we don't have to compute this whole sorted subarray sum, but let's keep it here for reference. In the previous approach, when we are trying to create the subarray sums array, we were actually iterating the values from left to right and then accumulating the sum in the nested loop, right? And let's add all the elements in the nums array to the min heap. Then what is the minimum element we get from the heap? That is 1. That also corresponds to the sorted subarray sums first element as well. Then what is the second minimum element we get? That is 2. Similarly, that also matches with the sorted subarray sums second element. Then for the third element, we get 3, which is also matching the sorted subarray sums third element. But now, if we remove the element from the min heap, we will get 4 instead of 3. So how are we getting 3? And the way is we actually add 1 plus 2 equal to 3, because that is a subarray sum between 1 and 2. So when we remove 1, we should also add back 1 plus 2 to the heap. Similarly, when we are pulling out 2 from the min heap, we should also add back 2 plus 3 to the heap. So this is how the sequence will look. When we are pulling the element from the min heap, we sum it up with the adjacent element on the right and add it back to the min heap. So for that, we will also need the index of the element which was actually popped out from the heap so that we can get the adjacent element. So how about we actually save the sum and the index pair in the min heap instead of just the number. So this index will be storing the point at which we have actually calculated the sum so far. So for example, when we pop out 1, let's assume this is a 1 based array instead of 0 index. So this will be 1, 2, 3, 4. So these are the index. So when we are actually adding back 3, we are adding sum 3 at index 2. So similarly, when we actually pop out this 3 next time, we will get 3 back as a sum, and then we see 3 as an adjacent element as well. So we will get next sum as 3 plus 3. So we will save 6 at index 3. So we will generate the sorted subarray sum by picking up the minimum element from min heap and then adding the adjacent element back to the heap. But now let's apply this in our problem. So we need to sum the subarray sums between indices left and right. So anything we generate before the left index, we actually don't add it to the sum, but we will add it to the min heap so that we can continue to generate our subarray sums. And anything between the left and right index, we can actually just add it up to the sum and continue to add it to the min heap as well. But anything more than right index can be ignored. So as soon as we know that we have generated the right number of elements, we will just stop the algorithm. Now let's see this in action. So initially we will add all the elements to the min heap with the corresponding index. Since we are using 1 base index, I am adding 1 at index 1. Similarly 2 for 2, 3 for 3, and 4 for 4. Now what is the minimum sum we can pull out from the min heap? That is 1, right? So because this is the first element and left is equal to 1, so this lies between left and right. So we will use it in the sum. So we will add 1 here to the sum and add the corresponding next sum back to the min heap. So we will now add it to the adjacent number, that is 1 plus 2 is equal to 3. So we will now add 3 and the corresponding index 2 to the min heap. Now the next element we pop out from the min heap is 2. So we will again add it to the sum because it's in the range. And now the corresponding adjacent number in the heap for 2 is 3. So we will add back 2 plus 3, that is 5, back to the heap at index 3. Then we pop out 3 as a minimum element, right? So we will add 3 to the subarray sum. And the next index of 3 is 4, right? So we will add 3 plus 4, 7 as a sum, and it will be at corresponding index 4. Now the next element we pop out from the min heap is 3 at index 2. So that is 1 plus 2 equal to 3. It is the fourth element and it is still in the range 1 and 5. So we will add it to the sum. Now number of elements we have added is 1, 2, 3, 4 so far, right? And left was equal to 1 and right is equal to 5. So far so good. So we removed sum equal to 3 and index equal to 2. So now index after 2 is 3 and at index 3 we can see that the value is also 3. So we will add it to the current sum. 3 plus 3 will be equal to 6. So now we will store 6 at index 3 for the subarray sum 1 plus 2 plus 3. So now the next minimum element for us is 4. So we will pop it out from the heap. So then it becomes 13 as a total for us. And we have reached right equal to 5. So we will now stop. We have now generated the sum between all the subarray sums between left and right indices. And in terms of space complexity, we can see that it is O of n, where n is the number of elements in the nums array. Because at any point, we are just storing O of n elements in the heap. So that is the space complexity. And in terms of time complexity, because pushing and popping one element in the min heap takes log n time. And we are doing it for right number of elements. So it will be right log n. In the worst case, again, right can be equal to n squared. But in the average case, maybe right is less. So that's how we get a slight improvement in terms of time complexity. Now let's jump into the code part. So maybe first thing we can do is define the pair class where we can store the long value for sum and the corresponding index value and just provide the constructor to it. Now we don't need this subarray sums at all, but we can reuse this for loop to add the values to the priority queue. That is our min heap. Let's initialize the priority queue. And in the priority queue, we can actually pass the comparator because it's a min heap. So we can just use the long dot compare on the sum value of the pair. And now we can offer the elements to the queue. So we will create a pair of sum and index. So sum is initially the number itself. So we can say it's like nums I, and the corresponding value will be I plus 1 because I'm using the 1 base index now so that we don't have to deal with the weird values in left and right. And now we don't need collection dot sort as well. We still need answer because I'm already using long here. So I don't need to use long here because I can take care of the overflow here itself. So now what we have to do is we actually start looping from I equal to 1 to right index in the inclusive way. So that's why we need the equality. So first thing we will do is we actually pull out the element from the min heap. So if I is greater than equal to left, we already have a limit on I less than equal to right. So that means sum generated is between left and right indices. So we should add it to our answer. So we will add answer is equal to answer plus sum percent mod, right? But this will convert it to long. So we will convert it back to int. And this is how we will actually update our answer. Now, when we push back the element to the priority queue, we have to check whether the current index is less than n or not. And the reason is suppose we have nums array like 1, 2, 3, 4. And suppose for 3, we have already added 3 plus 4, that is 7 to the min heap. And then we popped out 7. So should we push back anything after popping out 7? And the answer is no, because we have already added all the subarray sums for this element. And now if you try to add something, we will get index out of bounds. So to avoid this, we should also have a check if the current index is actually inside the bounds. If yes, then we will increment the current sum by adjacent value on the right. We will also increment the current index by 1 to move to the right. And we will offer it to the queue again. That's it. And now we will just return the answer like we were returning. Let's run this code. Hopefully there are no typos. And speaking of typos, so it should be current.sum. My bad. Let's run this code again. Cool. Let's submit this code. Awesome. Think it improves the code time complexity a bit. So I hope this video was useful to you. If it was, please like and subscribe. Sorry for a bit long video today. The code link with both the approaches is in the description below. Have a nice time. Thank you.